Picture the scene that every science fiction film has sold you for decades. A dusty red landscape stretching toward a horizon that feels almost familiar, almost terrestrial, almost like home. A gleaming spacecraft sitting on a launch pad, engines warming, countdown clock ticking towards zero. Brave explorers strapping into their seats, exchanging confident nods, preparing to fire their engines and arc gracefully back through the void toward a pale blue dot waiting patiently in the dark. The music swells, the rockets ignite, the journey home begins. Now, let the mathematics speak. Because the universe does not compose dramatic soundtracks. It does not care about narrative arcs or the emotional weight of a homecoming. The universe operates on an entirely different register, one written in the cold, absolute language of orbital mechanics, thermodynamic debt, and kinetic energy exchange. And when you translate that language honestly, the comfortable science fiction fantasy of a casual return journey from Mars dissolves into something far more sobering, far more awe-inspiring, and in many ways, far more beautiful for its brutal honesty. Getting to Mars is an extraordinary achievement. Getting back is a physics problem of an entirely different magnitude, one that exposes every fragile assumption hiding beneath the surface of our most optimistic dreams. Consider this image. Imagine a deep-sea diver who has descended alone to the very bottom of the coldest, most pressurized oceanic trench on this planet. The journey down was brutal, months of preparation, a complex machine sustaining every breath, a careful, calculated descent through crushing darkness. But the diver made it. The diver stands at the bottom, mission accomplished, surrounded by an alien landscape of extraordinary strangeness. Now, imagine that to return to the surface, this exhausted, starving diver cannot simply ascend the way they came. Instead, they must collect sand and compressed water from the trench floor, use these raw materials to construct a highly volatile chemical rocket entirely from scratch, ignite this improvised vehicle with perfectly calibrated thrust, and then blast upward through the entire weight of the ocean above them, not losing pressure control, not losing fuel, not losing thrust at any single moment during that ascent. The ocean does not negotiate. The crushing weight of the water column above does not grant exceptions for courage or ingenuity or the emotional significance of wanting to go home. It responds only to one thing: sufficient energy applied with sufficient precision, delivered without a single catastrophic failure. Mars is that ocean. Its gravity well is that crushing column of water. And the mathematical price of ascending out of it is not a rounding error that clever engineering can quietly ignore. It is the central, defining challenge of the entire return mission, and it begins with an equation that aerospace engineers have quietly referred to for over a century as tyrannical. Konstantin Tsiolkovsky derived the rocket equation in 1903, and in its beautiful, compact form, it conceals a truth of almost savage severity. The mathematics demonstrates that the mass of propellant required to achieve a given change in velocity grows exponentially with the velocity demanded. This is not a gentle, linear relationship. It is exponential. It punishes ambition with geometric ferocity. To lift a meaningful payload off the Martian surface and achieve the velocity necessary to escape Mars and begin the journey back toward Earth, you require an engine producing enormous thrust, and you require propellant, vast quantities of propellant, far more propellant by mass than the payload itself. You cannot carry that propellant from Earth. The mass penalty of transporting enough fuel for the return journey across interplanetary space makes the initial mission effectively impossible with any propulsion technology we currently possess. The fuel for the return vehicle must therefore be manufactured on Mars itself using Martian resources before the crew ever arrives. This sounds, on its surface, like a clever solution. It is, in practice, a battle against entropy conducted on a frozen, hostile world with no margin for error. The process is called in situ resource utilization, and the specific chemistry involves extracting carbon dioxide from the thin Martian atmosphere and reacting it with hydrogen, either carried from Earth or extracted from subsurface ice, to produce liquid methane and liquid oxygen. The Sabatier reaction and related electrochemical processes can accomplish this in principle. In principle, on Earth, in a warm laboratory with reliable power grids, with spare components readily available, with engineers who can walk outside for coffee and return to a functioning facility. On Mars, you are manufacturing rocket fuel in an environment where the average surface temperature hovers around minus 60 degrees Celsius, where dust storms can blanket the surface for months and reduce solar power generation to near zero, where every mechanical component is operating at the absolute edge of its engineered tolerance with no possibility of replacement delivery. A single failure in the liquefaction system, a fractured seal in the storage tank, a compressor motor that seizes during a dust storm, any of these events does not merely delay the mission. It eliminates the mission permanently. The return vehicle becomes a tomb precisely as cold and permanent as the planet surrounding it. This is the first wall, the thermodynamic wall. The crushing reality that generating the energy currency necessary to purchase your way out of a planetary gravity well requires a manufacturing operation of extraordinary reliability conducted in conditions specifically engineered to destroy reliability. Assume for a moment that this wall is overcome. Assume the fuel is produced, the spacecraft is fueled, the launch day arrives. You have now encountered the second wall, and this one is not made of chemistry. It is made of geometry, it is made of time, and it is absolutely mathematically immovable. Earth and Mars are not stationary targets waiting politely for spacecraft to arrive at their convenience. They are moving objects, orbiting the Sun at different velocities along different orbital paths. Earth completes its orbit in 365 days. Mars requires 687 days. The geometry of their relative positions is therefore constantly changing, and the energy-efficient trajectory from Mars back to Earth, the Hohmann transfer arc that curves gracefully through space using the minimum possible propellant, is only available when the planets occupy specific relative positions. This window opens approximately once every 26 months. 26 months. That is the rhythm of the solar system. That is the clockwork of celestial mechanics, completely indifferent to human scheduling, completely deaf to human urgency. If your return vehicle is not ready on that precise date, if your fuel production fell behind schedule by 2 months, if a medical emergency required postponing the launch, if any of 1,000 variables conspired to slide your departure date past the geometric window, then the next available low-energy return trajectory does not open for another 26 months. And there is no physical mechanism by which additional propellant can meaningfully alter this constraint for a chemically propelled spacecraft. The energy required to force a trajectory that deviates significantly from the Hohmann transfer is so enormous that it exceeds the capacity of any vehicle that could have been landed on Mars in the first place. You cannot simply burn harder and overcome the geometry. The orbital parameters are fixed by the masses of the Sun, Earth, and Mars, and the laws of gravitation. They are as permanent as the laws themselves. Missing the window by hours produces the same result as missing it by weeks. The mathematics does not offer partial credit. This is the temporal trap. This is the moment where the comfortable cinematic fantasy of departure on demand collides with the absolute rigidity of celestial clockwork and shatters completely. You are on Mars not merely until your mission is complete. You are on Mars until the solar system decides to offer you a geometric corridor home. Now consider what happens to a human body during the time between arrival and that corridor opening. Mars has a gravitational field approximately 38% as strong as Earth's. This sounds merely inconvenient. In physiological terms, it is catastrophic on timescales of months. The human body is not a static structure. It is a dynamic biological machine constantly calibrating itself to the gravitational environment it experiences. In reduced gravity, bone mineral density decreases. The rate of loss in microgravity is well documented from decades of International Space Station research, approximately 1 to 2% of bone mass per month in critical load-bearing skeletal structures. The muscles responsible for posture and locomotion atrophy at similar rates. Cardiovascular function degrades as the heart adapts to the lower demands of a reduced gravity circulation regime. Martian gravity, while stronger than microgravity, is insufficient to prevent this biological degradation over mission timescales of a year or more. An astronaut who has lived on Mars for 18 months arrives at their return vehicle in a state of significant physiological compromise. Their bones are less dense, their muscles are weaker. Their cardiovascular system has recalibrated itself for a lower gravity world. Now, this person must survive atmospheric re-entry. Re-entry into Earth's atmosphere is not a gentle process. It is controlled violence. A spacecraft decelerating from interplanetary velocities generates deceleration forces of several times the gravitational acceleration at Earth's surface. These forces are applied to the human body in the precise direction most likely to pull blood away from the brain, creating the conditions for loss of consciousness and cardiovascular stress in even a well-conditioned, fully healthy individual. Astronauts returning from long-duration space flights on the International Space Station, where exercise protocols are far more comprehensive than anything achievable on a planetary surface, routinely require physical assistance simply to stand after landing. A Mars return crew is not arriving from 6 months in microgravity with access to daily treadmill sessions and resistance equipment. They are arriving from an extended planetary surface stay, followed by a return transit through deep space of approximately 7 months, during which galactic cosmic radiation continues its relentless biological accounting. Radiation exposure during a Mars transit exceeds permissible career limits established for Earth-based nuclear workers. The cellular damage accumulates. The increased cancer risk is not theoretical. The neurological effects of long-duration radiation exposure are still being actively studied, but the data suggests that cognitive performance may be measurably affected. This is the biological wall, the point at which the physics of the universe and the physics of the human machine intersect in ways that transform the final moments of a triumphant return into a physiological crisis of the first order. 3 walls: thermodynamic, temporal, biological, each one independently formidable. Together, they constitute a physical architecture of extraordinary severity, one that does not yield to optimism or willpower or the narrative demands of a story that needs a happy ending. And yet something remarkable happens when you sit with this reality long enough to stop fearing it. The profound difficulty of returning from Mars does not reveal the smallness of human ambition. It reveals the true scale of the universe we inhabit. It reveals how spectacularly improbable it is that this particular planet, orbiting this particular star at this particular distance, with this particular atmosphere and this particular gravitational field and this particular magnetic shield, produces creatures capable of looking outward and recognizing the barriers that separate them from everywhere else. Every time you stand outside on an ordinary evening and feel the air on your skin and the full weight of a one-gravity world beneath your feet, you are experiencing a physical environment of such precise and generous calibration that the escape price alone, the mere energetic cost of leaving, staggers the mind when calculated honestly. Earth is not merely comfortable. It is the solution to an equation so complex that the rest of the observable universe has not, as far as we can determine, produced it twice. The mathematics of orbital mechanics, of gravity wells and thermodynamic debt and biological thresholds does not diminish the explorer. It illuminates, with cold and perfect clarity, precisely what the explorer is up against, and therefore precisely what the explorer represents when they choose to go anyway. That is not naive optimism. That is physics making a statement about the character of the beings who study it. The universe has constructed barriers of almost incomprehensible scale between worlds. And somewhere on a small blue planet in an unremarkable spiral galaxy, creatures made of that same universe decided the barriers were worth understanding, even when understanding them most clearly meant confronting the possibility of